this is the basic idea with radiometric dating, is that you have to, there's two things you got to do, you got to be able to do. You need to know the original proportional of unstable nuclei, and then you have to measure the current proportion. So for example, and the one that everybody knows about is radiocarbon dating, right? And there is carbon-14, right? Right, and carbon-14, I believe, undergoes a beta decay and becomes nitrogen-14, which is just ordinary nitrogen, right? Okay, carbon-14 is created in the Earth's atmosphere, I think, by cosmic rays, right? So there's this certain proportion, it's vanishingly small, of the carbon dioxide you inhale, and that becomes part of your bodies, and that the plants inhale, and it becomes part of their bodies, right? Okay, is this carbon, and almost all of it is just regular carbon, whoops, that number's supposed to be a 6, there we go, right? Almost all of it is carbon 12, right? Okay, but here's the deal. You only have carbon-14, it only is ingested into your body when you're alive, correct? Okay, so as soon as you die, or as soon as a plant dies, or a piece of wood or cloth or something like that, right? A piece of the Shroud of Turin or something like that, right? Okay, as soon as that's no longer a living thing, it doesn't absorb carbon-14 because carbon-14 is part of the Earth's atmosphere, and so only living things absorb it, right? Okay, and so as soon as that thing dies, this stuff starts going away, right? And so what you can do is you can know, there's ways to predict exactly what the level is of carbon-14 in things that have just died, right? It's a plant, wood that you've just cut, you can measure this thing, and you can compare these things. This has a half-life, I think, what is it, 10,000 years or something like that, right? You can look it up, or no, it's 5,730 years, right? Okay, and so you can look up this half-life, and by knowing this relative proportion, right, of course, as time approaches infinity, that proportion is 0, right? There's none of this stuff left, right? At 5,730 years, it's half of what it currently is, right? And et cetera, et cetera. And then the thing you need to know about radiocarbon dating is that there's actually two different ones. There's the old one and the new one, right? The old one was inaccurate. Somebody actually made a correction, and I think it has to do with solar cycles or something like that. So maybe it's not just cosmic rays, maybe it's sunspots or something like that. I'm terribly ignorant, but there is a correction for it, right? And so the old dates, I believe, made things older, and now they're not quite as old, or something like that. But that's the notion there. Then the question is, and this will only work for things, in the tens of thousands of years, right? And so, yeah, it doesn't work for like the age of the Earth or something like that, right? So what you need to do, yay. Okay. What you need to do for rocks, right, is you need to look at the when rocks solidify. Some of them make these pure crystals, right? Well, when in the crystalline process, in the formation of these crystals, the crystals are nearly pure because of the way they fit together, right? And so, as stuff comes out of the Earth's core, it's got this particular ratio of radioactive to not radioactive nuclei, two different isotopes, right? It's got a particular ratio of these, and some of these guys have half-lives of billions of years, right? Okay, and so what you can do then is of course, once it hardens into a pure crystal, it's no longer getting supplied with those radioactive, short-lived, relatively short-lived things, right? And so as soon as it hardens, the clock starts, right? And then you can date it from there. You can look at the ratio of the radioactive ones to the not so radioactive ones, right? The stable ones. Now this is an interesting story because there's an isotope of lead that has a half-life of billions of years, right? And so the person who came up with the Earth's age, okay, actually was the person that figured out that we were poisoning ourselves by putting lead in gasoline. Yeah, this is kind of a funny thing. Okay, this guy also invented the clean room. Here's the story. Okay, what he'd do is he would get these samples of lead. Now, to do this, when you measure this ratio, this is vanishingly small. The ratio of these radioactive things is really, really small. So you have to do very, very careful measurements, right? which doesn't mean it's not valid. It just means you've got to, there's an uncertainty, but we've got to minimize that uncertainty, right? We've got to do very, very careful measurements, right? And so he's measuring lead. He would get these samples in the field, he'd put them in his car, drive them to the lab, measure them, and almost every time these samples were getting massively contaminated with lead from some unknown source. Ordinary lead was contaminating these samples, right? And pretty soon the guy figures out that the lead is in the air. Lead is in the air that we're all breathing, right? There's enough lead in the air to contaminate these samples beyond recognition in their transit from the, as soon as you get them out and put them in the air, oops, game over, right? You know, so he actually gets a way to get the samples, keep them isolated. Then he's got to, in order to work with them in the laboratory, he's got to filter out the lead from the air. So he makes a clean room with these incredible microfilters. People going in have to wash and they have to put on clothing to keep the lead that they're bringing in with them off of them. And of course, where's the lead coming from? Cars, yeah. We put lead in gasoline. It was an additive to gasoline, right? So you can look at this. It's what was it called, tetraethyl lead or something like that, right? Okay, and you can look at this graph, and it's like, you know, no lead. You can go back, and then people later did this. They went back in the Earth's, in the ice samples. You can go and look at atmospheric air trapped in the ice, right? And you can go back, and it's like there's no lead, no lead, no lead, no lead. Then we invent the automobile, still no lead. Then we need tetraethyl lead, and it's like, you know, right? You know, and so. You know, gee, lead is not a good thing because your body doesn't like metabolize it, doesn't get rid of it, and it will kill you, right?
Lead, like, just decay in
No, not all lead, right? You know, so you know, so this is the crazy thing, right? There is a radioactive type of lead, and this was screwing up his measurements, right? So he'd actually discovered that this, you know, the lead levels in the atmosphere are just going up and up and up, right? Of course, as soon as the automobile and chemical industry was told of this, they immediately said, oh, gee, this is a menace to society. We'll stop doing it, even though it'll cost us money. Or did they, just like the cigarette companies, fight it tooth and nail? Everybody needs lead, you know, it's, I don't know. Okay. Oh, yeah, I guess they had to be forced. They had to be forced. Isn't that funny? Okay. It's amazing what money does to people, right? Okay. So he invents the clean room. And eventually, I believe he gets the Earth's age to be 4.5 billion years, which is an interesting thing.
Right.
Yeah.
How do they date dinosaurs if they're too old?
Oh, yeah. They don't do radiocarbon. They're dating them. There's lots of ways to date them, right? The main way to do this, there's a lot of ways, right? But you can take the rocks. You can date the rocks that you find in amongst that, right? But a lot of it's just stratigraphic dating. They know the fossils basically. Right now, what you do is you just look for certain fossils because there's certain little critters that evolved at a fairly predictable rate, and so you just look for in that layer of stuff these particular fossils, right? And then that is backed up with all sorts of other things, right? Ultimately, it gets down to, I believe, radiometric, and yeah, I mean, there's lots of ways, right? There's also the reversal of the Earth's magnetic fields, right? There's what's that thing? It's called the wood, you know, the tree rings, right? There's an amazing effort to actually take the tree rings, and there's good years, bad years, right? And that tends to be global, right? So you can look at wide tree rings and match them up. They're using statistical methods. So there's a lot of overlapping things that people have done to date the Earth. But the very best thing, I don't know if I've ever, I think I've told this story. If somebody tells you that the Earth is 6,000 years old, yeah? Tell them that it's 47 years old. No, it's actually 48 years old. It was created on the morning of November 1st, 1962. Yeah, we've talked about this, haven't we? Yeah, this is a good. Yeah, don't take them on their terms. Take them on your terms. You know. No, because I was born before that.
But all those memories were just planted at that time. Yeah.
What about World War II? Also created at that time. All memories, all evidence. There we go.